All right. So we'll start by drawing our picture and trying to figure out what quadrant we're in. So I notice that theta is positive because it's between 11 pi and 12 pi. So I'm going to be going around doing my rotation counterclockwise. So 0, pi over 2, pi, 3 pi over 2, 2 pi. Then we go over to 3 pi, and then 4 pi, and then 5 pi, and then 6 pi, and then 7 pi, and then 8 pi, and then 9 pi, and then 10 pi, and then 11 pi, yay, and then finally to 12 pi. So going from 11 pi to 12 pi is this piece down here. Amy, so far so good? Okay. Next, we're going to do all silly turtles crawl to decide where cosine is positive in those two quadrants. So clearly cosine is positive in quadrant 4. So my theta here is 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, and to my answer. So there's my theta. Yikes. Amy, so far so good? Yeah. Okay. And then my alpha is going to be here, the piece made by the x-axis and my terminal side, the acute angle, I should say, formed by the x-axis and the terminal side. So since the last axis that theta crosses was vertical and theta is positive, I know I'm going to be subtracting alpha. Okay with that? So theta is going to equal the end of the x-axis that alpha is on, and then it's going to be minus alpha, where alpha is cosine inverse, absolute value, 0.19. Amy? So this is my angle that is alpha, right? I'm going to be using that end of the x-axis that makes up alpha. That's where that number is coming from. Is that okay? Yeah. So if alpha was on the other side, I'd be using the 11 pi. Does that feel okay? Yeah. So it's just kind of a visual. And then it's just calculator time. So 12 pi minus cosine inverse of 0.19, but I think I had to change my calculator to degree mode earlier today. Yep. So I'm going to put it back into radian mode there. So when I do that, I get 36.32. And just to check this, I'm going to make sure that when I plug that in for cosine, I get 0.19, which I do. And then I want to make sure that number is bigger than 11 pi, which it is, but still less than 12 pi, which it also is. So we're quite convinced that we have the correct answer. Does that feel okay? Yeah. Perfect. Natalie?
Can you go to number 4?
Okay. So again, we'll start by kind of drawing our picture. So 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, and then 7 pi over 2. So we're looking at quadrants 2 and 3. So to figure out which one of those two quadrants I need, all silly turtles crawl. I'm looking at where sign is negative. So that would be quadrant 3. So if I draw my theta then once around and then to my terminal. So far so good. I'll draw my alpha, which is going to be here. And then since the last axis that I passed was the horizontal and theta is positive, I'm going to be adding theta. So what should I be adding theta to? 3 pi, yes. The other end of the x-axis, or the end of the x-axis that's used to make my alpha. And in this case, alpha is sine inverse the absolute value, 0.86. So 3 pi plus sine inverse, sine inverse. And I don't do the absolute value in the calculator, I just do that part in my head. So 1046. And just to check, sine of 1046 is negative 0.86, that's good. Should be bigger than 5 pi over 2, which it is, and smaller than 7 pi over 2, which it is.
That made a lot more sense.
Yep. Katie, I saw your hand up earlier.
Yeah, YouTube number 9.
Sure. Okay. So I'll draw my picture, 0 pi over 2 pi, 3 pi over 2. So we're looking at quadrants 2 and 3. Using all silly turtles crawl. Quadrant where tangent is negative is quadrant 2. So far so good. I'll draw in my alpha. Since the last axis we passed was the vertical, I know I'm going to be and theta is positive. I know I'm going to be subtracting alpha. So pi minus alpha. Where alpha is tan inverse, absolute value 3.25. And now it's just calculator time. So I get 1.87. If I do tangent of that, I ought to get negative 3.25 back, which I do. That number better be bigger than pi over 2, which it is. but smaller than 3 pi over 2, which it is also. So I know I've got it. Sure thing. Jack, did I see your hand come up again?
Yeah. Could you do number 8, please?
Same sheet?
Yeah.
Okay. So this one's going to be a little bit different because we have to go backwards. Notice that in this problem, theta is negative. So remember, when we're going backwards, we're going clockwise instead of counterclockwise. So we have 0, we have negative pi over 2, and we have negative pi. So we're looking at quadrants 3 and 4. Using all silly turtles crawl, I'm looking for where cosine is negative. That's in quadrant 3. And when I draw my theta, again, I'm also going to be drawing clockwise around. So far, so good? Okay. I'll draw my alpha. And now, to write my equation, I notice that the last axis that theta went through was vertical, but because theta is negative, instead of subtracting alpha, I'm really going to be adding. So I'm going to have negative pi plus alpha. Where alpha is cosine inverse absolute value negative 0.62. So negative pi plus cosine inverse 0.62. I did the absolute value in my head, just FYI. So I get negative 2.24. And then if you wanted to check this, cosine of that number is negative 0.62. Clearly that's smaller than 0 and bigger than negative pi. Negative pi is just negative 3.14. So, Eddie?
So on a test, per se, or quiz, would we be allowed to like add 2 pi's to the original equation and then not have to do it like like just do it normally? Like
Sure. Yeah, that's okay. So again, on the answer key, so over the years I've changed kind of the way that I've taught this. So the answer key is old, using a method that I kind of stopped using because it ended up felt like it was more confusing for students than just doing everyone the exact same way, where we're not like adding or subtracting different amounts. But certainly you can do that same way that I showed the work on the key, and that's certainly fine. Yep. Lily.
Number 12.
Okay. So again, we'll start by drawing our picture. Again, noting this is negative, so we're going clockwise. So 0, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2. In fact, I'm going to stop doing the negative half ones. So that's negative 3 pi, and then negative 4 pi. So we're looking at something in quadrant 1 or 2. Using all silly turtles crawl, looking for where tangent is positive, I'm going to be in quadrant 1. So drawing my theta, then I go around to negative 2 pi, and then to my terminal. So there's my theta. So my alpha is here. Since the last axis I passed through was vertical and theta is negative, I'm going to be adding alpha. So theta is negative 4 pi plus alpha, where alpha is tan inverse of absolute value, 1295. negative 4 pi plus tan inverse 1295. So negative 1107 is my answer there. And if I wanted to check that, tangent of negative 1107 does give me the 1295. Negative 1107 is bigger than 4 pi and smaller than negative 3 pi. So we're good. Does that feel okay, Lily? Amy?
So when you're putting in like the absolute value in the equation, should we just like take away the negative sign if it's there, or is there something like type in calculator to make it the absolute value?
I mean, I just take away the negative sign
Okay.
because, I mean, you can type it into your calculator. If you press math and then go over to the number section, there's that absolute value command. But like, that's a lot of buttons to press when I can just elect to not put a negative sign in there.
Okay. Thank you.
So I just usually do it in my head because it's way faster to me, you know, but whatever, you can do it that way too. Eddie?
When we calculate in radians, is there ever going to be a situation where it won't like fall under the certain range, or would that only be like in worksheet 1 when we have to deal with like, stuff on the
Okay, I'm confused at what you're asking me again.
So
Can
you
you
know
sh-
how like for example for like question 4 7.32 is like
Question 4
yeah
on this sheet.
yeah
Okay.
you know how that's like greater than 3 pi over 2 and then less than 5 pi over 2, or greater than 5 pi over 2 and less than 7 pi. Would there ever be a situation where that is not true? Like
Where there's like no solution.
yeah.
I mean, if I pick a goofy range, I can certainly make it have no solution, but I would not be doing that intentionally. I mean, I guess I could make a mistake and have something like that turn out, or like make a mistake and there's actually 2 answers inside of the range or something. But the goal would be to not have no solution right now. Now, when we start doing solving trigonometric equations, that could be certainly something where that's a valid thing to have happen, but right now, no. Is that
That makes sense.
okay? Cool. Anybody else? Cool. Well, let's move on then, folks. So today we're going to talk about sections 4.2 and maybe start section 4.3. So in section 4.2, we're going to start with 2 pieces of vocabulary. Those 2 terms are angle of elevation and then angle of depression. And I'm going to just kind of define these with a picture because that's really going to be how we're going to be using this sort of thing. So imagine you have 2 people, one person at an elevated position to the other. Now, assuming that they're just standing with their line of sight straight forward, So that's the person on the ground's line of sight. And this would be the person on the cliff's edge line of sight. Everybody's okay with that? So say we're talking about the person on the ground, and they raise their head to look at the person on the cliff. So their line of sight is moving up. We call this an angle of elevation. Everybody's okay with that? Say you're the person on the cliff. To look at the person on the ground, you have to tilt your head down. So your line of sight is moving downward. We call that the angle of depression. Everybody's okay with that? Geometrically, what can you say about this angle of elevation, this angle of depression? They're the same value. They're congruent. Does anybody remember why they're congruent? Yes. They are alternate interior angles. So when you have two parallel lines cut by a transversal, we know that the alternate interior angles are congruent. Now, it's not important that you remember the names of these things or remember that verbatim. That's not important. The fact that you remember that the two angles are the same would be the important thing. You don't need to be able to justify that. But it's something we did know once upon a time, so I felt like it's worth making mention of. The one thing that I want to say that's critically important here, the place where most students make their mistake, notice that the angle of depression is not here. That is the place where most students want to put their angle of depression. So just be cognizant of that. I'm warning you now. Okay. Let's run through a couple of examples, and that's going to close out section 4.2 for us. Okay, doke? First example, Christy is looking up at the Fisher Building in downtown Detroit. She's standing 200 feet from the base of the building and finds the angle of elevation to the top of the spire to measure 66 degrees. How tall is the Fisher Building? So I'm just going to basically draw a really simplified version of the picture. And I'm going to assume that any structures are going to be perpendicular to the surface of the ground, unless you're specifically told that that is not the case. I think that's a fair assumption to make. Now, we know one building in particular that's not perpendicular to the ground. The Leaning Tower of Pisa would be the one that I'm thinking of. But in general, it's usually considered a desirable trait to have your building perpendicular to the ground. And even the Leaning Tower of Pisa was not built that way intentionally. I think it just had the ground underneath it. There was like a collapsed or whatever. Okay, and we're looking for how tall is the building. So basically what this story problem boils down to is we have a right triangle that we know an angle and a side form. We're looking for the length of another side. What would I use to solve this kind of a problem? Yeah, I'm going to be using SOHCAHTOA, right? And specifically in this case, looking at the angle theta that I know, I have the adjacent side I know and the opposite side I'm looking for. So I can say that tan 66 is equal to opposite over adjacent. I can multiply both sides by 200 to get the x by itself. And then it's calculator time. Note that for the previous set of problems, my calculator was in radian mode. What mode should my calculator be in for this problem? Degree. How do I know it should be in degree mode? 66 degrees. It says right in the problem that, hey, dummy, we're using degrees. So I get 449.2 feet. Questions on that one? Pretty easy, right? Not a big deal. Probably drawing the picture is the hardest part. Let's do another. So here it says Jane has climbed a tree and is looking down at her friend Mary. Jane has climbed 17 feet in the air, and the angle of depression to Mary is 49 degrees. How far is Mary standing from the base of the tree? Now, remember that this is an angle of depression. So the 49 degrees is actually out here. It's not inside of the triangle. Now you can see how easy it would be to make that mistake, right? And just want to put the 49 there next to the J inside the triangle. Got to be careful. So one of two things I can do here to get an angle inside the triangle. I could call that angle 49 using alternate interior angles. Or I can observe that this angle has to be 41 because it has to add to give you 90 degrees. Either is okay to do. You don't need to do both. Either one is going to give you the correct answer. But that's how you end up getting an angle inside of the triangle. Either way is okay. Is that okay? We're good? Okay, so just like the previous problem, we use SOHCAHTOA. In this case, which one would we want to use? I know opposite. I'm looking for adjacent. I better use tangent. Everybody good with that? Solve for x. I'll multiply both sides by x to get out of the denominator. And then divide both sides by tan 49. And then calculator time. So that's about 14.8 feet. What do you guys think on that one? Not too bad, right? Yeah. Not too bad. Last example here. This is the most difficult one. So Claude and Simone are riding bicycles in Paris. Isn't that romantic? At one point, they look up and measure the angle of elevation to the top of the Eiffel Tower to be 32 degrees. Everything I like to do on my romantic trips to Paris. When they pedal 100 meters closer to the tower, the angle of elevation changes to 37.5 degrees. How tall do they estimate the Eiffel Tower to be? Okay. So that's our picture, right? Everybody agree with that? Notice, though, with this picture, there's no right triangle where we know a side and an angle in, right? Because we're missing this piece in any right triangle that we try to build. Everybody observe that? So what we're going to do instead is we're going to think about this as two separate right triangles with two variables in them, create a system of two equations, and solve that system by substitution. So the first triangle I'm going to make is going to be the big triangle. So what is that adjacent side of the big triangle got to be? It's got to be 100 plus y. Everybody's okay with that? The second triangle I'm going to make is this littler one here. Actually, do that so you can still see that the other triangle is that. Everybody okay with the two right triangles that I've drawn there from the picture? From the first triangle, I can say that tan 32 is equal to opposite over adjacent. From the second picture, I can say tan 37.5 is equal to opposite over adjacent. And I'm going to try to solve for x using substitution or elimination. Now, when I look at this, computationally, I'd prefer to solve for x directly here rather than finding y first, because really the answer, I don't care about y, the answer I care about is x. The problem is that algebraically it's going to be kind of a pain in the buttocks to solve for x first. So I'm going to end up solving for y first. I think it's easier that way. So for the first equation, I'm going to multiply both sides by 100 plus y to get rid of the fraction. And in the second equation, I'm going to multiply both sides by y to accomplish the same thing. Notice at this point, both of these two equations, both are equal to x. So I can set them equal to each other. Everybody go to that? Now I have y's on both sides of my equation. To solve this for y, I'm going to have to get those y's on the same side. So I'm going to distribute the tan 32 through. Then I'm going to subtract the tan 32 from both sides to get the y's on the same side. Now I notice on the right-hand side of my equation, both factors contain y. So I'm going to factor a greatest common factor of y from the right-hand side. Still doing okay? And then lastly, I'm going to divide both sides by tan 37.5 minus tan 32. And now it's calculator time. Now, typing this into my calculator, I'm going to use the fraction command rather than a bunch of parentheses. So I go alpha y equals, and then choose that numerator over denominator command. So I have 100 times tan 32 over tan 37.5 minus, tan 32. Notice that that allowed me to just type it in exactly as it looks like on my sheet of paper. So that gives me 438.6 for y. Unfortunately, I didn't want to solve for y, right? What I'm really looking for was x. So I'm going to go back to this equation, plugging in this value for y to solve for x. So that's about 336.6 feet. Nope, meters. Now that one algebraically was a bit of a pain in the tuchus, but geometric or trigonometrically it wasn't too bad, right? Like all we did was right triangle trig in there, and we just had a crummy system of two equations to we had to end up solving, but you know, not the end of the world. Those of you that have been to Paris, what do we got, about 1,000 feet tall, the Eiffel Tower? I don't even know. Is that realistic? It's probably close. What do you guys think? Parisian fans? That feels pretty tall. But I don't know. Maybe it's really tall. I don't really know. Never been there. What?
984 feet.
Okay, so that's pretty darn close then, right? I guess those numbers were semi-realistic for somebody who was estimating the angles of elevation from their bicycle. That's not too bad, Claude and Simone. Okay. That puts a wrap on section 4.2. In 4.3, we're going to start this today. We won't finish it. In section 4.3, we're going to talk a little bit about applications. One of the important applications for trigonometry is it allows us to take a complex movement and break it down into like easier to deal with components. So for example, if we had like point A and point B, we could describe going from point A to point B kind of following that path. Or we could describe going from point A to point B by going like, you know, some amount to the right and then some amount straight up. These are both sets of directions are going to get us to point B. One of these two routes may be simpler computationally on how to kind of describe a complex set of directions that involve like lots of different turns. But that's kind of what we're going to be, where we're going to kind of be going with this in this section. So in particular, we're going to be interested in kind of these navigational type questions or situations where we're describing going from one location to another, or a series of locations even. Now here's the crummy part. These people that are navigators have their own separate way of describing an angle. So let's start by defining what that is. So they use the term course or bearing. So the course or bearing of an object is given as an angle of the object's line of travel measured clockwise to north. So the course or bearing of an object is given as an angle of the object's line of travel measured clockwise starting from due north. Ugh. Is that the way we describe angles in trigonometry? No. So one of the first things that we're going to have to worry about is going to be describing or being able to translate from a bearing into a standard position angle. Because all of the mathematical tools that we have kind of require us to use a standard position angle. So that's going to be the first task here. So we're going to start by just talking about how we convert a bearing into a standard position angle. So let's say we have the bearing alpha that is equal to 58 degrees. So I'm going to start by drawing myself a picture. So north, east, south, west. My bearing starts at due north and goes clockwise 58 degrees. So that's my alpha. Everybody's okay with that? My standard position angle, I'm going to refer to that as theta, starts at the positive x-axis and goes counterclockwise. So if alpha is 58, what does theta have to be? 90 minus 58. Very good. So that's 32 degrees. We feel okay on that? Okay. Let's say this time our bearing is beta, or 164 degrees. Well, we're going to start the same way. So starting from due north, so we go 90 to here, and then like 74 more to there. And then our standard position angle is like this, right? Everybody's okay with that? So, well, let's label this. Red is alpha, blue is theta. So let's see, the standard position angle is 90 for that quadrant, 90 for that quadrant, 90 for that quadrant, plus this little sliver in here. What's that little sliver gotta be? 90 minus 74, or 16. So theta is just gonna be 90 plus 90 plus 90 plus 16. So 286. Is everybody okay with doing that? If I'm going too fast, holler at me to slow down, or if you have a question about something, speak up. Amy.
Should we just explain again how you know to like count all three of the 90 degrees? Or like, do you always just do that, or just depend on how many times you're going around?
Yeah, so it depends on how many quadrants I'm traveling through, right? From there to there is 90. From there to there is 90. From there to there is 90. And then I have the 16 more. So it's purely from where the terminal side is in my picture.
Okay.
Is that okay?
Yep.
Yeah, no problem. Okay, let's do another. So this one will say gamma is the name of our bearing, and it's 221 degrees. Do you guys like all these Greek letters you're getting? Ooh. Chemistry. Okay, so we'll start our bearing from due north. So 90, 180, like 41 more. So far, so good. And then my theta is here. So that's 90, 90, and then 49 more, right? So theta is 229. Oh. One more. Say delta is 299. Let's see, we go 90. 180, 270, and then like 29 more. $90, $90, $90, and then 29 more. And my theta is 90, and what's this one got to be? 61. So theta is 151. What do you guys think? Does this feel okay? All right. Let's actually stop here. This is probably the best place to stop. I don't want to get into another one of these problems here. 90 plus 61.
Oh,
The stuff in blue.
Okay, so it's just like the stuff, that's all it is.
Yep.
Oh, alright.
Yep, that's all I'm doing is adding up the theta parts. All right, let's talk about what the schedule looks like here for the rest of this week and the next. So there are just 3 sections to chapter 4, so we're in the last section right now. Dun, dun, dun. So we'll plan on finishing section 4.3 Wednesday. Friday, the asynchronous day, will probably be the review day that you'll kind of work on your stuffs. Next week, on Tuesday, we'll take questions from the review and then start chapter 5. And the following Thursday will be the test day for chapter 4. So it gives you a chance to ask questions since you won't really see me on Friday. Does that all seem reasonable? What haven't we done yet? Homework quiz. If we're asynchronous on Friday and the test is next week, when do you think that homework quiz has got to land? Probably. What do you think is going to be the topic?
But we did so far.
Without having gone over 4.2? Probably 4.1. Yeah.
It makes sense to me. I'm okay with it. I'm okay.
Wait, we didn't go over 4.2.
Correct. Why would we have a homework quiz over something we haven't gone through yet?
Oh, I'm thinking about worksheet.
Worksheet 2, yes.
Oh, that's why. Okay.
4.2, no. 4.2 we learned today. Worksheet 2, yes. Worksheets 1 and 2 were all homework